up. Hopefully you guys are hearing. All right. So you guys can hear me okay?
Yes.
All right, very good. So let's just, I'm gonna kind of go, it's one of those things, I might be on borrowed time. So sometimes the Zoom software does not play well with some of these labs. And so when that happens, it's just a matter of time and I'm gonna start being garbled again. So, all right, so as Harmon said, I'm on the bottom of page 2, and I was about to show you the plot of the voltage versus current data. So again, I did 2 of them for you. Let me share my screen. All right. So as I said last time, I put all my data out. There's going to be 4 sets of data all together. I put them all on the same screen. And this is what we're doing here on the bottom of page 2. These 2 lines. And so as usual, you would highlight them, do a scatter plot where I chose connecting lines. And so that particular plot just looks like this. And it's just voltage versus current. You can see there's a nice line associated with it. All right, and so again, you'd want to turn in something that looks like that to me. Again, I make sure you remember to label your axes. So going to the top of page 5, one of the things we want to try to do is calculate the slope of the curve. How does the slope relate to with resistance? And so I'm going to stop sharing. So going back to my whiteboard, again, we see that that the plot shows that there is definitely a nice, almost perfect linear relationship with this curve. And so what are we actually seeing here? Well, we are seeing, again, I'm on the top of page 3. We're seeing voltage versus current. Okay, so voltage versus current. And we're seeing essentially a plot that's a line, as we see. Now, what is the slope? Well, quite honestly, we have V equals, we always say V equals IR, right? Let's just write it as V equals RI, just for the purposes of this. Well, we see we have a Y equals MX plus B kind of ratio, or really a Y equals MX relationship, if you will. Going back to algebra, where your slope is resistance. I mean, you have a voltage versus current curve, and the slope of this curve is going to be, and again, this kind of looks like a Y equals MX relationship. I mean, there's not even a B here. And that slope is your resistance. So the resistance is the slope. So looking at this, the resistance, better. The slope of the curve is the resistance. So the slope of the V versus I curve is the resistance. Well, again, you'll have on the bottom of page 2, you'll have 5 data points, and I only went through the first 2. But again, if they are all belonging to the same line, you just have to pick any 2 points you wish. Right, 2 points determine the line. Algebra 1. So we can just pick either just 2 points in it. Right? Heck, I can just pick the points that I selected. And so let's do that. And so let's see. I have 2 data points. I have voltage and voltage and current, which is what I went through with you. And I showed you I picked 1.5 volts and I picked 3 volts. And as current, I had 0.150 amperes, and I have 0.300 amperes. All right. And so if you just do this, you essentially say, well, I know that in algebra, change in Y over change of X, right? Well, it's a change in V over the change in I. And again, we can kind of cross multiply and say we have pretty much a delta V equals I, delta IR, right? We have an Ohm's law relationship. So I pick my 2 points. I have 3 volts minus 1.5 volts divided by 0.300 amperes. Again, these have to be in volts and amperes, minus 0.150 amperes. And of course, as I would expect, I get 10 ohms. And 10 ohms, it was that setting that I selected on the resistor slider board. So again, that you'd want to do a calculation like that in problem 5. You want to first of all state, well, that's what this is. The V versus I curve is going to give you a slope that is the resistance. Here's what the resistance is, and notice that it does agree with what's on the slider bar in the software. And then the other question is, well, what would happen if you if instead of being 10 ohms, what if the resistance was 50 ohms? What would your curve look like? Anybody want to answer that? What happens if it was 50 ohms on the slider bar? The curve be steeper or shallower?
Would it not be more steep?
It would be definitely more steep. So instead, I would have, if this was my 10 ohm curve, again, always, this was 10 ohms, you'd have a 5 times steeper, if I could draw that, something like that. That would be a curve. Again, it's not drawn to scale, but that would be probably like your 50 ohm. It's going to have a slope that's about 5 times greater than the slope of the original curve. Again, it doesn't look like 5 times, but imagine that it is. So definitely a steeper curve. Okay. Number 6 is pretty tedious. So what you're going to do in number 6 is you're going to fill out. So again, I'm going to let you do most of number 6 here, but what you're going to do now is you saw those other plots or that other data that I had in my Excel spreadsheet. Well, it came from filling out number 6. All right, and so let me go back to the software. And let's see. Go back to my share. Okay. So you should see the software. So on the far right column, you take a resistor setting. So for instance, I would pick 800 ohms. So try to, sometimes I have a hard time getting on exactly what I want. See, it's very touchy. I got 800 ohms earlier, but right. Yeah, it's right. All right. I probably won't. I did get 800. Bear with me.
So it's okay if we get close to 800.
That's fine. Yeah. So we'll just go with 804. If you did 804, you're gonna do this yourself basically. But again, it's fine. No, I'll try one more time. All right, 799. That's pretty close. All right. We'll say that's 800, or well, it's 799, of course. But I'd write down. I'd probably just cross out the 800 that you see right there. And if let's say for instance you got to 799, you didn't quite get 800. I would just cross it out and say you got 799 ohms instead. That's perfectly fine. But you're gonna make a resistor setting. I had a lot of trouble with the resistor slider bar. The voltage slider bar I had no trouble with at all. The resistance slider bar is just I could not get 405 ohms in the second part, and I could not get 40 in the second part. No matter how hard I tried, I couldn't do it. I got 800 this morning, but I couldn't get the other two. So all you're gonna do really is you're gonna map out data. So you see the far left column, you'll start off with about 0.1 volts, and then you'll just fill out what the current is. So again, that current is saying it's 0.1 milliamperes, right? Well, again, you want to write it in amperes. You're going to divide that by 1,000. So my cell says 1.0 times 10 to the negative 4. and I divided by 1,000, it's, you know, and it has to be in amperes. And that's a reminder. So that's in milliamperes. Now, luckily the voltage is in volts and the resistance is in ohms. So that's good. But the current, remember, is in milliamperes. So again, to get it into amperes, you need to divide by 1,000. All right. And so, now, the next, so what do you do now? Well, you record that. I mean, I'd record 1.0 times 10 negative 4. I would pick 2 volts. I would just pick 2 volts on the slider bar. Notice the V gets bigger and bigger. It's kind of cute little little effects here. You know, your bigger your V goes higher, and the bigger your V, the bigger the letter V gets. You know, so anyway, well, you see here. Oops, I have. Yeah, so I see that I have 2 volts now, keeping the resistance the same, and I'm going to get something like 2.5 milliamperes. What would I put in my second column? 2.5 times 10 negative 3. And then, you know, I maybe pick 3 volts. And I'd write down 3.8 times 10 negative 3. And I would continue going 4, 5, 6, 7, 8, 9 volts. And then when I got done with all of that, I would try to find 405 ohms. Now, as I said, I got 407 I did earlier. Oh my God, I got it. No, I got 400. Yeah. I got a 405. Bingo. All right. I couldn't get that this morning to save my life. All right. All right. So I hit 405. This time I couldn't hit 800. All right. And then you're going to do the same thing, right? And so you're going to develop yet another set of data. So again, you'll have the first the first 10 measurements are going to all be for 800 ohms. Then the next 10 measurements will all be for 405. So again, you start off with, there we are with 0.1. You'll notice you have now 0.2 milliamperes. Well, you'd write in that particular corresponding cell 2.0 times 10 negative 4. And then I would pick, 2 volts. And then, what would you write? 4.9 times 10 negative 3. Again, you want to write in amperes. Do one more. 3 volts. 7.4 times 10 negative 3. So on and so forth, right? You'd fill out the next, numbers. And then you'd want to, when you got done with that set of data, you'd bring it down, bring the resistance down to about 40, if possible. I settled for 38 this morning. We'll settle for 39 now. I'm not even going to try. This thing is so touchy, the resistance slider bar. Yeah, this software needs some improvements, but it's pretty good. Again, you're going to go back to the beginning again, a new set of data, and you see 0.1 volts. It's going to correspond to 2.6 times 10 negative 3. 2.6 times 10 negative 3 on the ampere on the current. 2 volts. Again, what would I put? 5.13 times 10 to the negative 2 amperes. Do one more. 3 volts. 7.69 times 10 negative 2 amperes, and so on and so forth, right? So it's really just filling out this data table. All right, and if you turn the page to number 4, or page 4, number 7, what number 7 wants you to do is it wants you to calculate the resistances analytically for all this data. So what you're going to do is you're going to, well, number 7, first of all, says we want to graph this data. All right, so I'm going to stop sharing this, and I'm going to graph. Share my Excel here again. All right. should see an Excel spreadsheet, do you?
Yes, we do.
Awesome. So going back to my data tab, you'll notice that that there are 3 more sets of data. I just put them in here as well. This set of data correspond to 800 ohms resistance. This set of data for 407, that's the best I could do this morning. I didn't get 405. This set of data, 38 ohms. I mean, I got, this time around I got 39 ohms. But again, I just basically, put all the data in the table and then just copied it. And again, the current is in the left column, the voltage is in the right column, right? And so each one of those, I just had to essentially do the same thing. I highlighted the 2 columns, insert, and then I selected the chart. I selected the not this scatter plot, but this scatter plot over here that has the lines in it. I mean, I'm not going to do a trend line. I mean, it's going to be a pure line. There's no need for a trend line. This is about the most perfect lab data you've ever seen, right? So trend line, you're not going to see it. So anyway, I laid out these plots by themselves. This is my voltage versus current for 800 ohms, the way I labeled it. This is the voltage versus current for 407 ohms. And this is the one for 38 ohms. And basically just three linear plots that you'll want to turn. So you're all together, you're gonna turn in a total of 4 of these straight line plots.
Are those slopes always going to be the same?
Oh, they're not the same. The way this thing's Excel is, they're not the same axes. That's the problem. Excel tries to be smart and say, oh, let's just make your axes, nice and fitting. I should have changed the axes. You can kind of see the change in the slopes, but those slopes will, again, the data is Excel tries to help you out by giving you nice axes that are I guess smart or best for you, but these are definitely vastly different slopes.
It just looked deceptive.
Yes, they do look. But if you look carefully, like this, the axis here goes from 0 to like 30 or 0 to. It looks like it goes from 0 to. It should go from. Hang on 1 second. That data, let's see, the voltage goes, oh, okay, yeah. So the voltage goes from, the voltage goes from 0.1 to 9, but the current will go from like 2.6 on 10 negative 3 to 0.238. So it's going to look, the current here is about a factor 10 greater than the current right here. And so if you kind of look at the vertical axes will be the same each time. They're all going to be basically 0 to 10, because I'm taking the voltage readings from 0 to 10 each time. What's different is going to be the current axis. So and again, it's hard to see on this graph, but the range on the currents. I mean, your plot is set up such that it goes from min to max, and it overall ends up looking like the same plot. But the voltage. The voltage or y-axis is the same on all of them, because you're doing the same voltage readings, that the current will be different. So yeah, these will be vastly different slopes. So you'll basically in this you'll turn these in, but really problem 7 here on the top of page 4 is nothing more than taking 2 data points in each, so taking two data points for each of your sets of data and calculating, the resistance values for each plot. So when I did it, I just picked second. Oh. Go to my here we go. I hit a weird button here. All right, so back to my whiteboard here. So when I did it, I just, I picked, again, I'm going to pick 3 slopes. I have 3 sets of data. So the way I answered question 7, again, I'm on top of page 4. The way I answered question 7 is I did as well. I have R1, which is a delta V over a delta I. And as usual, I mean, I picked between 2 volts and 3 volts each time. So my top was always 3 volts minus, so in this case, 3 volts minus 2 volts, which is my top for each one of my calculations. And I found out, when I did it, I found out that my corresponding current data was 3.8 times 10 to the negative 3 minus 2.5 times 10 to the negative 3. And these are amperes. And I found out that my R1 for that set of data ended up being 7.70 times 10 to the second ohms. Now, my actual resistance was 800. The problem is when you get into the milliamps, when you convert those amperes, you end up losing precision. The larger your current gets, the better your precision will get. So again, you're going to see more error when you have the smaller currents. When I did R2, my second set of data, again, same deal, delta V over delta I. When I did that, I had, again, on the top, I picked the same 2 data points. I picked 3 volts minus 2 volts. That corresponded then to 7.4 times 10 to the negative 3 minus 4.9 times 10 to the negative 3 amperes. And then my R2, when I did it, I got 400 ohms. Again, not so, I mean, because these are small, relatively small currents, I really had 407. But when my currents got bigger, like R3, delta V over delta I, now my currents became bigger. So again, it's going to be the same 3 volts minus 2 volts, taking the same data points. This time I had 7.89 times 10 negative 2 amperes minus 5.26 10 negative 2. And that time around, I found out that I got 38 ohms, which is what I actually had in the setting. So the problem you have is that what the slider bar output gives you, it only gives you 2 decimal places of precision at the milliamp level. Okay, so you get better precision the bigger your current. So you're gonna have better answers. So this is really a factor of the readout from the software. I mean, it's fine. It's you go to your pencil and paper and do a real calculation, you'll find out you'll get a better answer. But this is what you get. This is from the software. It's essentially artificial error being implemented or input into the or introduced into the problem by the software itself, by the lack of precision in the software. So again, this is what you get. You're off by a little bit. You can't really do a very precise calculation or measurement with the software. You're limited. So sometimes you're limited by your lab equipment when you're going face to face, or you're actually doing real physical labs. Sometimes you're limited by your software. So okay. 8. Again, this is kind of a little bit of repetition here on page 4. 8 is basically, what is the physical meaning of the slope of the current voltage graph? Again, the physical meaning is the resistance. Again, these graphs, their physical meaning is resistance. Why? Because, again, for the same reason, V equals IR. I would just explain it the way you explained it before. This is kind of number 8 is kind of a duplicate question of some sort. Number 9, I kind of answered for you already. I told you about R equals rho L over A. So essentially, the question number 9, bottom of page 4 is, is it possible to decrease the resistance of the wire without changing the material, what it's made of? Yeah, you can change the geometry. Well, I want to decrease the resistance. Again, I'm just saying this, you want to write it, but again, the resistance is rho L over A. So if I to decrease the resistance, not change the material, I think we want to decrease the resistance. Yes. We can make L shorter, that decreases it, or A larger. Again, tell me what, in your own words, what are L and what are A? I mean, maybe draw a little picture, and just don't write rho L over A. Tell me what these actually mean. What is A? Well, it's a cross-sectional area. What is L? The length of the resistor. And it's made out of what? It's made out of a material that has a resistivity rho, like I said before. I answered, I'm on the back page, page 5. I answered query 1 already. Ohmic materials, material that obeys Ohm's law. Questions 2 and 3. Again, as you change the balance, so let's kind of think about these a moment, or maybe I should just let you think about them. I mean, the idea is, as you change the value. Let me ask you. See if somebody here wants to answer this question. As you change the value of the battery voltage, okay, I'm going to change it to a different battery. Change V. How does this change the current through the circuit and the resistance of the resistor? So what effect, so essentially, if I change out the battery, I put in a new battery, so does that affect the resistance? I put instead of a 5-volt battery, I put in a 9-volt battery. Does that change the resistance? So the answer is no, right? The resistance has to deal with geometry and the material. Again, the resistance is always going to be rho L over A. I'm not changing the material of the circuit. I'm not changing the resistivity is the same, and I'm not changing the resistor at all. So the resistance, I mean, I pick a resistor off the shelf and I look at it. Yeah, I know you are 100 ohms or you're 250 ohms. I mean, irrespective of what kind of circuit I plug it into, the resistance is not going to change. But the current, well, that will. Why? Because the current is epsilon over R. So if I change the battery, I definitely will change the resistance. Or sorry, I'll definitely change the current. Will not change the resistance. Resistance is a constant, but I will change the current. Okay, so say that in your own words. Number 3, as you change the value of the resistance of the resistor, how does this change the current through the circuit and the battery voltage? All right, so now, second question is, okay, I go back to this, and now I'm going to change the resistance. I'm going to put in another resistor, but I'm not going to change the battery. So does the voltage change? If I have a 100 ohm resistor or a 1,000 ohm resistor, does the voltage across this resistor change? Anybody?
Yes.
It does not. Remember, Kirchhoff loop rule. Okay, I have some epsilon minus IR equals 0, going all the way around. Well, epsilon, so again, all this tells me is that I is epsilon over R. Well, if I change the resistance, epsilon does not change. And what is the voltage across here? Voltage across resistance is the same as epsilon. No matter what, Kirchhoff's loophole guarantees that voltage, because I only have one resistor here, that voltage is the same across these two equipotentials is the same as it is here. So irrespective of what the value of the resistance is, the voltage across it will not change. However, the current will. Again, the current, as we know, this was the original observation made by George Ohm, is that, you know, his very observation was that some materials seem to have more resistance than others. Some materials, if I have a large resistance, then I have a not so large current. If I have a small resistance, I have a big current. So again, if I change the resistance, I'm absolutely going to change the current. I mean, that's the whole point of Ohm's law. All right, and so again, these are the kind of thinking questions. But so yeah, I'm basically done. Unless you have any other questions. I mean, this is a relatively easy lab.
Hey, Professor.
Yes.
I had to go into work on Tuesday, so I missed the review. I know sometimes you cover some of the bonus questions. Did you cover any while you were doing the video on Tuesday?
Yes. I'll ask your friends the questions and see if they help you.
Okay.
So who's the American scientist and statesman who is known for the conventional direction of electrical current?
Ben Franklin.
Benjamin Franklin. Yeah, it's also on the $100 bill. So Benjamin Franklin's one of them. And then who is the German mathematical prodigy? We have one Maxwell equation named after him, a statistical bell-shaped statistical distribution named after him, and he was one of the most accomplished mathematicians of all time. Carl Friedrich Gauss. So again, I'll write that down. Yeah, Carl Gauss is an interesting guy to look up. He had incredible mental powers. I mean, unlike most people, I mean, probably the smartest guy, probably smarter than Newton. But yeah, he was doing calculus by the time he was 4. Carl, maybe 5. Friedrich Gauss. So there's a few people in history that are like this. They're called mathematical prodigies. One of them is Gauss. Leonard Euler's another one. Euler's method. I mean, Euler's another one. Norbert Wiener. He went to Harvard. He was 9 years old. We have Wiener filters. You know, electrical engineering. You know, Norbert Wiener's another one. Yeah, there's a number of these mathematical Mozarts right there. Carl Gauss is probably the greatest of all of them. He was just a little boy, and doing mathematics, greatest mathematician in the world probably by the time he was 5. I think Newton, he was born in 1777. So Newton had already passed away, so Newton wasn't there to compete against him. So yeah, Gauss was probably the best in the world by the time he was 5. But yeah, he's one of those gifted people. And then the other questions on the bonus are just units. What are electrical units? So if you're really careful about your electrical units, like unit of resistance, unit of current, unit of voltage, things like that, that's all I'm going to ask you there. I mean, these are the only, so Benjamin Franklin, Carl Gauss, those are the only 2 people on that are people questions, and the rest of them are electrical units.
Okay. Thank you.
You bet. Any other questions? Every so often you get in. Oh, and this lab is, because you have an exam next week, this lab is not due next Friday. It will be due the following Friday. So you get a little break there. I think, what is that? The next Friday is October 2nd. I think the following Friday is October 9th. So this lab is not due until like the 9th.
And the homework stays the same. It's still due on Wednesday.
Well, the homework for this week, we are, I'm going to send an email about this, but again, the chapter 22 is humongous. It's the biggest chapter in the entire book. That's our chapter this week. And in fact, if you look at the lesson plan, it covers 3 days. It covers all this week and it covers half of next week. And so because of that, you also do not have homework due next week either.
Okay.
That homework is due, let's see, calculation here. I think September 30th for that one. I'm sorry. It would be due September 30th. It's October 7th. So yeah, so the next homework, the one for this week, the one that for this week's chapter 22, would be due October 7th, and the lab, the one I'm just got done talking about, would be due October 9th. So again, you have a little break there. It's a break for me too, because I need to get caught up with the grading.
Awesome, thank you.
You bet. Any other questions?
Hey, Professor, I've got a question for you.
Yes.
So I, all of my notes and my book and everything is on my, I have an iPad Pro that has a pencil. So all of my, and matter of fact, I'll probably take my test on my iPad Pro.
That's fine.
So that way I can just send it to you. I know you had mentioned earlier about not having a cell phone, but when I take the test on Thursday, I want you to know I'm probably still going to have a screen in front of me because I'm going to be writing on it.
That's fine.
Is that okay?
Yeah, I mean, thank you told me about it. It's all good. I mean, yeah,
I just didn't want there to be a doubt about that.
No. What I just don't want is, you know, if you ever watch Who Wants to Be a Millionaire, I just don't want someone doing a phone a friend or something.
Oh, right. Okay.
Yeah, so that's all I'm trying to prevent. I mean, there are people, I'll have at least 1 or 2 students every semester who lives on their iPad, and that's fine. I mean, and if you're one of those people, that's smart. That's good. That's the way you save a few trees. That's good too. So yeah, I'm all right with that.
Well, and it makes it easier to email you at that point.
Oh yes, indeed. No, it's all fine with me. Like I said, I just want to. And now, normally, if we're meeting face to face, I'd want you to write everything out on the paper. I would provide you the paper test, right? But here it's like, that's why back when I was meeting face to face, like Candace had me face to face. I mean, she could tell you. I would give reviews that were very much watertight. It would be all the problems done by me, but at the same token, you would not be allowed to bring anything in except the one side of a 3x5 card. But here I can't enforce any of that, so hence I'm leaving it to you to kind of do some of the work on your own. But at the same token, it's either problems that you've already done. Those would be the Cutnell Johnson problems that I suggested to you, or problems that I've done in the videos, which would be the OpenStax problems. So again, it's review on your part, but it's not extra work. It's just a matter of like, okay, let me go to that video. What's he talking about there? Let me go look at that again.
Thank you.
Mm-hmm. You bet. And it's over chapters 18, 19, 20. So I know we've already covered 21 and we're covering 22 this week. But again, those are 21, 22 are for the next exam 2. So again, this is only, I try to make things bite-sized. There's enough stuff in 18, 19 to 20 to keep you busy. So. Was this lab pretty easy? Was this lab pretty easy for you guys?
Yeah, not bad at all.
Yes, it was nice.
Yeah, it was one of those things you can play a video game and do the lab at the same time. I was like, wow, this is different. But it's an important concept, though. I mean, I just think I think this lab kind of hits you over the head with a concept that's relatively simple. I mean, it's simple but important. I mean, B equals IR is very important, but I think you're really, I think if there's one equation you'll never forget after doing this lab, is V equals IR. Any other questions?
No, that's it.
I think I'm good.
All right. Thanks, Candace.
Thanks, Professor. Have a good night.
You too. Take care.
Thank you. Good night.
You bet. DJ.